We were talking about eliminations in the last video, and we got to a point where we said, when the elimination happens and the double bond forms, we could get a choice, and that choice could be very important on what we write down as an answer, because one of them could be a major and one of them could be a minor product. And we talked about how to determine the difference between one or the other. So let's do another example before we move on in this video. And I'm going to go back to a ring structure because it seems like people are uncomfortable with rings, but they actually behave the same way, folks, as straight chains do. So don't let them intimidate you. You show them who's boss. And we're going to react this with H2SO4 and a little bit of heat. Okay, so here's the thing. There's going to be multiple choices that will happen here, and those multiple choices, there's going to be at least two of them. I know that because I see it coming, but I'm just going to go ahead and draw both of these versions down, okay? So here I'm going to draw a CH3 group and an OH group, and I'm just going to draw the same thing. This is my reagent that I'm starting out with. There's no difference here. It just kind of helps me preempt the product that begins to get formed. All right, so the sulfuric acid and the heat. The heat and the acid promotes elimination to happen. It could be phosphoric or sulfuric, it doesn't matter. So what will happen is that the OH will be targeted and whoop, off it goes, and it gets eliminated. Dehydration. But in order to dehydrate, we have to have a neighboring carbon, a buddy, that has a hydrogen to donate with. So in the first one, this is the carbon that had the OH group. Look at this buddy up here at the top. There's a hydrogen there. It's got three of them, right? So let's get rid of one of those hydrogens and let's replace it with a double bond. All right, so there's my first choice. A double bond could form between the carbon in the ring and the carbon that's sticking up out of the top. But that's not the only choice, is it? No, it's not. So in the second option, my OH group is going to be eliminated. Whoop! And off goes the bond. That carbon now turns to the buddies. And it says, hey, one to the left, one to the right, you're the same. It's a CH2 group no matter which way you go. So you got to give up a hydrogen. And they do. They have two of them. So I'm just going to target the one over here to the right-hand side. There is a hydrogen. There's actually two hydrogens that are right here. That carbon has 4 bonds in total. The hydrogens are not drawn. They're understood to be there. So one of those hydrogens, whoop, has to go away as well. So a dehydration reaction happens. That forms up a free bond to this carbon. This carbon has a freed bond up, and a double bond would form between those two carbons. Now, if I went left-handed, it would have been the same answer. It's the same molecule, believe it or not. The double bond to the left and the double bond to the right, it doesn't really matter. It's a symmetrical ring. There's no other weird groups on it and stuff. It's just a clean ring with a methyl group up at the top. So that's why there's only 2 different options here, not 3. Now, I've got to be able to pick out which one is going to be more preferred over the other. Can you do it? You want to take a stab at it? Well, in order to determine this, think about the substituents and the double bond characteristic. If you look at the double bond up here at the top, it's on a carbon that has 2 hydrogens. And this carbon is going to 2 carbons. So the carbon up on top is very exposed. Only hydrogens are there and hydrogens don't count. Well, what about down here? The carbon to the left, up here at the very top, it's got a methyl group and another carbon in the ring. And then over here, this carbon to the right-hand side, well, it's got a carbon in the ring, but the fourth one that's not drawn is to a hydrogen. So, folks, that one is more substituted. That one has more substituents than the top one. The top one has 2 hydrogens on an sp2 carbon. The one down below, only 1 carbon to an sp2 carbon. So out of these 2 choices, it's going to be this one. This one is going to be the most stable. Because of that, this one is going to be the major product out of the two different choices. And that's how we determine those possibilities when they exist. Now, things aren't so easy all the time, is it? No, you know that. You knew this was coming too, especially if you had me before. So let's take another alcohol. CH3, carbon, CH3, CH3, CH with an OH group, and CH3. And we're going to react this with sulfuric acid and some heat. Well, as before, I always draw the products, or the reagents, sorry. CH3, carbon, CH, CH3, a methyl group up here, and a methyl group down here. And we have an OH group that's there. Okay, so with sulfuric acid, story doesn't change. Sulfuric acid and heat promotes elimination. That OH group is going to be targeted. Whoop! Off it goes, and there we go. So this carbon now has a carbocation that is formed. Now, typically, we always look to the left-hand or the right-hand side. And we look at these options and we say, this is how we determine where our double bond is going to go. So if we look left-handed, folks, there's no hydrogen over there on that carbon. We need to pull a hydrogen off to dehydrate in the elimination. And this is just not going to work for us. So over on the right-hand side, we do have a hydrogen here. That hydrogen can be pulled off. And we can get a double bond that will form because of that. So this is a CH2 group that happens here, and this carbocation disappears at that point. So that is option number one. It's not the best option, though. This is a very minor product. I mean, I'm talking minor product. Why? Well, remember the foundational stuff that I told you it's very important that you'll never forget, and that kind of stuff is always going to hound you over and over? Here's one of those cases. So this is where we started. The OH group has been eliminated, but carbocation shifts can happen. These are E1 mechanisms. It doesn't see two things at one time. The steps do not happen all at once. They happen in individual steps. Carbon can make the decision right now to shift if it needs to. And the other examples that we've done, it's not had to shift because there's been no other better opportunity out there for it. I've just not mentioned it. But here we do. We have a better opportunity. If you look left-handed, that carbon is a better, more stable carbon because it could be tertiary. And right now the carbocation, it's on a secondary position. It's attached to two other carbons. But in order for this to shift, something else has to trade places. This carbon doesn't have hydrogen, but it does have a methyl group. So this methyl group will switch. So the methyl group will be shifted down, and that forms the carbocation at that new location that we didn't expect in the very beginning, right? So this is a 1,2 methyl shift. A 1,2 methyl shift happened because the carbocation had to be shifted down, and this allowed it to become in a more stable situation. Now we have a tertiary carbocation. That carbon is attached to three others. Now we can look at elimination. So this carbon, if I want to kind of talk about all the options, it's got a set of twins. Either one of these can donate to it. So in the elimination reaction, we could get an eliminated hydrogen here or there at the top. Doesn't matter. They both give you the same answer, and a double bond is formed at that spot. But that's not the best opportunity. So I'm going to erase that. There's a better option that's out there. Where is it? It's the carbon on the right-hand side. Look, that carbon has a hydrogen. That carbon can donate the hydrogen and say, okay, buddy, I've made room for you. Come on in. Stay with me for a while. So a dehydration reaction happens. That frees up a spot, and now a double bond can form between those two carbons. Why is that a better option? Because look at the substituents that are on the carbon. The carbon on the left-hand side, 2 methyl groups. The carbon on the right-hand side, 2 methyl groups. That is way more substituted than the other version. More groups are found on those sp2 carbons. And because of that, this is the major product from that elimination reaction. Number 1, we had to worry with methyl shifts. And number 2, we had to worry about the stability of the alkene. And the stability of the alkene is highly determined by how many alkyl groups there are on the sp2 carbons of the house. And there you go. There's the major product for that reaction. Now let's take a look at another example. Which of the following alcohols dehydrate faster when you heat them with acid? Oh, okay. We've talked about stability and terms of how reliable it is, willing it is to undergo an elimination. If I look at the OH group that's here, this OH group is on a carbon that is secondary. All right. So for part B, this OH group is on a carbon. It's attached to 3 others. This is tertiary. Oh, okay. That might be the dead giveaway right there. For C, let's move on. We have an OH group that's on a carbon. Oh, this is primary. That's the slowest one out of the 3 options, right? And then for D, we have this OH group. Oh, wait. This is tertiary. Well, I know that tertiary reacts faster than secondary, which reacts faster than primary. We've already talked about that rule. So here I have B and I have D that are both tertiary. What's the difference? Remember that thing I called delocalization? I told you it's going to hound you over and over. It's something that we talked about in Chem 251. Delocalization is present in one of these. How? Well, if this gets eliminated, a positive charge will form at that carbon. A carbocation gets formed. And look, right beside of that, we have a double bond. This sets up the rule of delocalization. Pi electrons move toward a positive charge. And because of that, I can turn my kids loose out in the front yard and let them run wild. Tell them to come back a little bit later. That improves the stability of the carbocation when it forms, because it's not just in one spot. That carbocation can move and it can be spread over that part of the molecule. Well, what that means is that it's more willing to get rid of the OH group, because the molecule knows when it goes away, it can handle that carbocation a little bit easier. So out of the 4 choices, which of the following dehydrates faster? It's going to be D. And that's because it's tertiary, but it's also because delocalization helps it out in the very end, versus something like B. That was tertiary too, but there was no delocalization there. No electron movement through the molecule. Once more, as I said, don't forget it. Stereochemistry really involves cis, trans, and E and Z. So in this example, you're seeing an alcohol, in this case 2-butanol. 2-butanol is going to get eliminated. You see the positive charge that begins to get formed. That positive charge, well, dehydration has to be, that molecule has to remove a hydrogen from it, some form, some fashion, and it's going to go inward to the left. So here we see groups that are on opposite sides, which is trans. And here we see groups that are on the same side, which is cis. Out of the two options, folks, trans is going to be more stable. The molecule likes that. Those groups are further apart from each other, and that improves the stability of the molecule, which means it hangs around more, which means we have more of it. So 74% split this time versus 23 and 3. Something else we need to talk about as well. Notice what we really talked about here were tertiary and secondary eliminations. These were E1s. That's the kind of groups that we've worked with so far. We've not really talked about primaries yet, have we? No, that's because we have to talk about them separately in a way. The primaries, they don't really break up. They cheat. They have an issue with being alone. So they always have to have a relationship to go with. And because of that, these are E2 reactions. They're a different type of mechanism. They're a cheater. So this carbon that has the OH group, it's going to get eliminated. That's the elimination mechanism. It's going to go away. But things are going to kind of happen all at the same time. It's not going to be by itself for a bit, and a carbocation shift is not going to happen. These prevent rearrangement. Wherever it is, that's where it's going to go. The issue, though, is with the primary alcohols and what they do. So we need to take a few minutes and we need to talk about these and really understand the difference with the E1 and the E2 mechanisms. So these are going to be for primary alcohols. So let's take our first one. CH3, CH2, OH, and I'm going to add on H2SO4 with a little bit of heat. What's the elimination product? Okay, well, this one's going to be pretty easy. You do them just like always, all right? I'm going to rewrite the reagent. There we go. So the OH group, whoop, goes away, and the neighbor carbon, there's only one, has to eliminate a hydrogen as well. So that turns into a CH2 and a double bond forms in between. There you go. Okay, well, what's so difficult about that, you say? I mean, if you gave me this alcohol and if you gave me this acid, this is what I would have done anyway, right? We eliminate the OH, we eliminate a neighbor carbon, hydrogen, and that opens up a site 4 double bond, and that goes in and it forms. That's my elimination product. Yeah, that's true. That's a primary alcohol reacting with an acid, giving us an alkene. Nothing surprising, right? Well, substitution can also happen with these. CH3, CH2, OH. And if I take a look at another alcohol group of the same thing, CH3, CH2, OH. Oh. What on earth? Why is this important? Well, this is an acid, and acid can protonate that alcohol as well. And that acid, if it does protonate the alcohol, turns this into a very good leaving group. And this OH could look at that carbon and say, you're up for the taking. And what we would end up with here is a CH3, CH2O, and then eventually a CH2 and a CH3. We've made an ether. And we've made an ether in terms of a substitution reaction. These are competing reactions with a primary alcohol. But here's the thing. This is the savior. It's this. The heat. Alcohols that are primary have more tendency to do substitution reactions. They are very exposed. Those carbons have very little neighbors around them. Because of that, they can sneak and cheat a little bit easier than someone that's in an apartment building where all eyes are looking out the blinds at all times. So substitutions are much easier for primaries. And substitutions could happen here, like the bottom route would go, because we're throwing it in some acid. And this is a possibility. But we're generating some heat. We're putting heat into the reaction as well. And that heat helps promote an elimination reaction to take place. So that's the number one thing. You have to have heat. But here's the other thing with primaries. You can get double reaction. What? A double? Yeah, well, let me show you. Let's say that we have CH3, CH2, CH2, CH2OH. And we react this with sulfuric acid and some heat. What would form? Just based on what you know right now, what would form? Oh, okay. So we'll redraw the reagent. CH3, CH2, CH2, CH2. There's the OH. So this promotes elimination. There's the right setup. So my OH, whoop, goes away. And the neighbor carbon, whoop, gets rid of a hydrogen. And that opens up the site for the double bond. And you would say, there you go. There's my product. And I would go, you're correct, kind of. That's actually not the true answer. Well, off of this, we have water, right? I mean, water got generated, dehydro, elimination. There you go. There's the hydro. There's the water molecule. So the issue here is that this is in acidic conditions. H plus is going to be present. And here we have an alkene yet again with H plus and water. A reaction can happen after this point. And that reaction would break the double bond. This elimination reaction targets the double bond. It breaks it. Two sites of attachment could open up. Hydrogen goes on one side that plays with the most H's. So hydrogen comes in and goes, no. Hey, you've got more hydrogens over here on the right-hand side. I'm going to play with you because that's how I am. I only want to play with people like me. And then that turns into a CH3. Over here to the left-hand side, this opens up my carbocation, which will eventually get my OH group. Okay, well, we still have sulfuric. We still have heat. So an elimination reaction still could take place, which means that that reagent, I'm just redrawing it, could become eliminated. Whoop! Off goes the OH group. And then this carbon's going to look at the neighbors and say which one's going to be better for me. And it's going to release that hydrogen there. That allows this double bond to have a more substituted group on each side of the double bond. And that improves the stability of that molecule. So this is something that we have to watch out for with primary alcohols. Primary alcohols are notorious for this. They will form these double bonds on the end. That's called a terminal alkene. And those terminal alkenes are so reactive because they're so exposed. They're at the very end. It's like a white flag that says, hey, come and get me. It's right here. And the presence of the water that's getting generated and the acid that's part of the elimination process could quickly, so quickly turn around and target that double bond and destroy it yet again to make a different alcohol. And that alcohol goes more inward. And then an elimination reaction can happen all over, and that forms a double bond that's more internal than terminal. And that internal double bond is more stable than the terminal double bond. So this is the problem that we experience with primary alcohols. Sometimes it's very difficult to stop it at that point of the terminal alkene up here. Very, very difficult for us to do that. So let's take a look at an example problem. Now that we know these eliminations are out there, let's take a look. What's the major product obtained when each of the following alcohols is heated in the presence of sulfuric acid? Okay, so that's the dead giveaway eliminations. They want you to eliminate here. And they want you to think about the major product if you have some choices. They want you to think about rearrangement if it can happen. If it's primary, they also want you to keep in mind there's a problem with primaries. It just doesn't really stop at one position. It actually reacts with itself again and shifts the double bond again. So let's just take a look at A first. All right, so with A, I'm going to draw out the structure. CH3, CH2, carbon, CH3 on top, an OH down here, and then a CH, a CH3 here, and a CH3 there. Okay, so we need to eliminate it. I'm not going to write down the arrow. I'm not going to write down sulfuric acid. I'm not going to write down the triangle for heat. We know that all of these are going to be the same. So we need to eliminate the molecule. All right, so that acid and heat goes in, looks at this OH, whoop, away it goes. And we form a carbocation here. That's a tertiary carbocation. Is it going to shift? The answer is no, it's not going to shift. It's tertiary. It doesn't need to shift. It's going to stay there. So it's going to look at its buddies, and it's going to go, okay, what's good for me? You know, how do I want to form this double bond? How do I want to make sure that I get as many substituents onto the double bond to make sure that it's stable? So the buddy to the left and the buddy up above and the buddy to the right are all different. I can draw 3 different products here, but I'm not going to. I'm going to pick the best one. If the double bond forms up above, that carbon is going to have 2 hydrogens on that side. Those hydrogens don't count as substituents. Okay, well, if I draw the double bond to the left, that carbon's going to have 1 hydrogen and a methyl group, and this carbon has a CH3 and an isopropyl group. So we've got 1 hydrogen there. That's pretty good, right? If I form the double bond on the right-hand side, I have a methyl and an ethyl over here on the left, and then I have a methyl and a methyl over on the right. So this is going to be a better option. That's where I'm going to put the double bond, because when I do that, this carbocation is going to be erased. That hydrogen is going to go away, and folks, those sp2 carbons have the most amount of substituents in these 3 possibilities. If you don't believe me, draw the other 2 forms down. Prove it to yourself. Those carbons end up with hydrogens on them. And this version, there's no hydrogen on either of the sp2 carbons. So as far as the major product goes, folks, this is it right there. You want to name this structure? Let's review some of the general chemistry or organic chemistry in 251 first. Let's name it. Longest carbon chain, 1, 2, 3, 4, 5. So this is going to be a pentane. There we go. And carbon number 2, that is where my double bond is going to be. Well, it's not really a pentane, though, is it? It's a pentene because that's where the double bond is located. So 2-pentene, we're getting closer. Carbon 2, carbon 3, carbon 4, carbon 5. Well, on carbon number 2, I also have this methyl group. And on carbon number 3, I also have a methyl group. So in the front of this, I need to put 2, 3, and then di, because there's 2 of them, methyl. 2,3-dimethyl, 2-pentene. That is the structure that we end up with the elimination of that alcohol. Now, what would be this alcohol's name? 1, 2, 3, 4, 5. So this is a pentane. Drop the E, add OL for alcohol. A number closest to the end that has the OH. And folks, no matter which way I go, 3 in from the left or 3 in from the right, it's going to be a 3-pentanol no matter what. So this 3-pentanol has some other groups with it. We have a group that's here and we have a group that's there. So by default, because OH was a tie, we are going to number closer to this end because that is a substituent and we like to give things lower numbers. So this is a 2 and a 3, 2, 3, dimethyl 3-pentanol. So 2,3-dimethyl 3-pentanol undergoes an elimination reaction. That elimination reaction is a E1 mechanism taking place in more than one step, allowing for carbocation rearrangement to happen if needed. In this case, carbocation rearrangement does not happen because that alcohol is on a tertiary position. When the elimination goes forward, the alcohol group and a neighboring hydrogen will be removed, and that will form a double bond, an alkene, as a product. That alkene that's formed is 2,3-dimethyl 2-pentene. Look at that. That was beautiful, wasn't it? Oh, that was music to my ears. We sounded so smart. If you understood that, if you followed that, you're learning alcohol reactions. That organic touch is still with you, and I'm so proud. So what I want you to do in the next video, before the next video, is to answer B, C, D, E, and F. Those are all eliminations. So put your knowledge to the test. Go through and attempt them. Try them. At least try them. If you get the wrong answer in the next video, you'll know that you'll get the wrong answer and you'll understood why you got the wrong answer. What decision did you make that was wrong? And then you just need to remember, just don't do that decision again. Right? We need to self-correct ourselves. So answer B, C, D, E, and F. And then come back, press play, and check your answers with mine. So good luck. All elimination. How hard can it be? Just remove the OH, right? Draw a double bond. Just make sure that you draw the double bond in the right place. I'll see you next.